Good afternoon, everyone. My name is Craig Wiegert. I am the department head of physics and astronomy here at the University of Georgia. And I'd like to welcome you here to the second of the talks that our distinguished speaker will be giving for us today. The first happened this morning over in our interdisciplinary STEM building, and I hope that many of you were able to attend that as well. I'm actually going to keep my remarks pretty brief. I'm going to introduce the man who will introduce you to the speaker. Dr. Johannes Abate is a professor in our department. He is the Dasher professor, is an endowed chair in this department. He works in the field of nano-optics and characterization of materials at very small scales, which intersects with the research that our speaker does. And I'd like to invite Johannes up here to talk a little bit about Dr. Betzig and introduce him to you before he gives you his talk. Johannes.
Good afternoon, everyone. Thank you for coming. We had a wonderful talk this morning at STEM building. This is the second talk and the last one for Professor Betzig. Professor Betzig is a professor of molecular and cell biology, the Eugene Cummins Presidential Chair in Experimental Physics, a senior fellow at Genelia Research Campus, and an investigator of the Howard Hughes Medical Institute at the University of California, Berkeley. Eric is also the 2014 Nobel Laureate in Chemistry, and as the lecture this morning, this lecture is also hosted by 3 different departments, including biochemistry and molecular biology, Department of Chemistry, and Department of Physics and Astronomy. This is also a signature lecture, which is from the Provost Office, and it's described as the following by Provost Hu. Signature lectures provide an opportunity for the university community to engage with nationally renowned speakers and learn from their wealth of knowledge and insights. This lecture series enriches the UGA learning experience by fostering the open exchange of ideas and deepening our interdisciplinary knowledge. And so we are very thankful to the Provost Office and particularly Provost Hu for selecting Professor Betzig's talk as distinguished signature lecture, as part of distinguished signature lecture series. I'm also very thankful to the various department heads who made this event possible, including the Professor Tina Salguero, Associate Head of Chemistry, Professor Craig Wiegert, our own department head, and Professor Chris West, the head of molecular and cell biology. And special thanks to Professor Alan Dorsey, who helped organize this event. I'm also very thankful to the following special people who helped out in many different ways, organizing some of the details that you don't see these people. This include Miss Netra Padek and Robin Taylor for help with setting up coffee and all other and lunch and that sort of thing. I'm also thankful especially to the undergraduate and graduate students of physics and astronomy, as well as student leaders, particularly the Committee of Undergraduate Students from my quantum mechanics class and the Ethiopian Student Association for a fantastic coffee. Those of you who are there could witness to that. Let's give a big round of applause to all these people. Okay, now very brief introduction to our distinguished guest, Professor Eric Betzig. Eric's research and interest impact is extraordinary in many different levels. His pioneering work includes near-field microscopy development, pioneering work in that area, as well as his contribution to super-resolution microscopy that is mainly used in biology. In the material world, we need to understand things at small scale in order to make sense out of them. and the near-field microscope has contributed significantly in that direction. Professor Betzig's main contribution for which he won the Nobel Prize is super-resolution microscopy, about which he will tell us a lot about today. His academic path is also extremely interesting. Those of you who were there this morning at the first talk probably heard some of the things, but just very briefly, he did his undergraduate work at Caltech in physics, and then went to Cornell to do engineering physics. And he particularly focused on, as I said, a pioneering work in near-field microscopy. And there he has always been thinking about, since those graduate days, to visualize molecular processes in biology, in biological systems. And these are extraordinary problems that have not yet been exhausted, but his contribution has made tremendous impact in this field, as you will see soon. He then went on to Bell Labs to continue his work on near-field microscopy. And then he, very surprisingly, we heard the story this morning in full, left Bell Labs, and for interesting reasons. I've had a wonderful interview with him this afternoon, so once the video is released, you would hear more about that. But he left Bell Lab because he sort of saw that the near-field microscopy had very little impact or had limitations for biology. And then he just quit completely academia and became unemployed and a homestay dad for several years. And during those years, he worked with his dad in his dad's company. And then after a while, he came back to academia again, but with much energy, with absolutely groundbreaking idea for super-resolution microscopy, for which he won the Nobel Prize. But again, it wasn't like the usual go to the lab and develop this. Instead, he teamed up with his best friend, Harald Hess, and then instead of going anywhere because they didn't have resources, they went to his friend's living room. And you heard this story from, the Steve Jobs story. That was very different from this one. This is actually much more impressive in my view. And built a microscope, did the first impressive work for which he won the Nobel Prize. So that is extraordinary story. And then from there, he were able to get a job, of course. And to make the long story short, he is now at UC Berkeley as a professor and Howard Hughes researcher. And we're very excited to have Eric with us. He's very busy, but he was silly and fool enough to believe me to take this invitation to come. He's been giving, I think this is what, the fourth sort of time he's talking to you guys. So I'm very excited he's here. Let's give him a huge round of applause.
That's the wrong one. All off. That's good. Nice.
Oh.
Doesn't that look pretty that way? Yeah, good. All right, good. Here we go. All right, so ever since humans were far enough along to look beyond their immediate existence, they started to wonder, how far away are the stars? How small is the smallest thing? Well, now we know a lot about how to answer that. So if we shrunk ourselves down by a factor of 1 billion, we would be about as large as the nucleotides in our DNA. However, if we grew ourselves by a factor of 1 billion, we would only be about to the orbit of the moon, which is about as far as humans have traveled, but obviously is a long way from the edge of everything. If we grew ourselves from that level by another factor of 1 trillion, we would be about at the size of our local group of galaxies, but that's only still about 1/10,000th of the universe. So we are about 1 billion times closer in scale to a molecule than we are to a galaxy. So when you ever think about that what happens to us is important, remember that we are just a little film on a tiny pebble in the midst of a vast emptiness, okay? So how do we know this? How do we know all this? Well, at first, the only tool the primitive man had was one, his own eyes. And so that same tool is used to look either small or big. When we look small, our cornea thickens and shortens in focal length, which allows us to discern features down to about 50 microns, or about the width of a human hair. If instead we flatten our corneas, we increase the focal length and look in the distance, that allows us with our naked eye to see about 1 arc minute of separation between two objects at a distance. However, the size that we can see on the small scale is still about 50,000 times bigger than the size of a molecule, and the resolution at the other limit is 50 times too coarse to see Neptune as a disk. So how did we go beyond that? Well, we build, as you can see in both of these cases, they're inversely proportional to the diameter of the pupil. So we need to make things that have bigger pupils. We call those things on the small end microscopes. We call those things on the far away telescopes. And so in either case, you make larger pupils that collect more rays over a much larger angle. So what is the history of going to these things and how are they connected? So in the 9th century, a Muslim polymath for the Iberian Peninsula, Abbas ibn Firnas, was the first to make clear glass, which could be fashioned into hemispheres called reading stones that would allow people to look at written words with better resolution as their eyes failed as they get older. By the 14th century in Europe, eyeglasses were actually fairly common to allow reading glasses to allow people to see. And then at around the dawn of the 17th century, Zacharias Janssen put together, instead of just one single lens, put two lenses together and realized that he could make a microscope that could see in a finer scale than just a single lens-based microscope. Just a decade after that, Hans Lippershey, who was a maker of the glasses that would go into eyeglasses, the actual lenses, he was working one day, and according to a probably false story, a couple kids took a couple of these lenses, and they went outside and they put them together like this, and they looked at a weather vane in the distance, and they realized they could see the weather vane much better than they could with their naked eye. And then Lippershey saw them out there and did it himself, and that was his eureka moment. So basically he made the first telescope, with a compound telescope with two lenses. So this, unlike the microscope, which kind of stayed fallow for a while, the telescope, which was initially called the Dutch perspective glass, took off like wildfire because it was useful for surveyors, it was useful for the military, it was useful for navigation, it had all sorts of uses, and so it took off right away. One of the first practitioners of this who heard about Lippershey's new toy was Galileo. And so Galileo immediately set about to make a telescope. Eventually he went from the 3x expansion that was common at the time to, under his hands, a microscope or a telescope that was 30x magnification. And when he turned that to the heavens, he made one discovery after another. First, he looked at Jupiter and found 4 little stars that were orbiting around Jupiter, which today we know as the Galilean moons. He looked at the moon, which was believed to be smooth, and instead he found craters and mountains. He looked at Venus and saw that it went through all the phases from full to new. And between the observations of the Galilean satellites and the observation of the phases of Venus, he realized this meant that the Earth had, and all of the planets had to go around the sun, and that other bodies would go around the planets. And so he was another proponent of the heliocentric vision. He wrote a book advocating for that, and then later on he was called to the Inquisition because he created a second book trying to supposedly objectively compare the heliocentric and the geocentric versions, but in the process he actually sort of made fun of the Pope inside of the book, and as a result he was under house arrest for the rest of his life. So Galileo may be the most brilliant scientist in all of history. It just goes to show that the better you are at science, the more likely you are to end up under house arrest. So, the telescope greatly improved over time in a sort of continuous fashion. Like I said, the microscope really laid fallow from the time of Janssen until around the 1660s, when two guys changed everything. The first was Robert Hooke, who was a polymath, who was a contemporary of Isaac Newton. The only problem is that while Hooke was just about as brilliant as Newton, they hated one another's guts, because Hooke was a very difficult man to deal with. He claimed to have invented calculus and so forth, and he was brilliant, and he did many, many things in his career. One of them is he was a terrific artist, and so he built what was at the time one of the best compound microscopes, and he looked at everything. One of the things he looked at was the fleas that was the cause of the bubonic plague that was sweeping through London at the time, and he put all of these artistic renditions of everything he saw in a book called Micrographia, which was the first bestseller, not the first scientific bestseller, the first best-selling book of all time. And he became famous for that, as well as many other works. And it also let the man in the street start to have an appreciation for what science could be. Before that, people didn't think about science at all of impacting on their lives. But that book really started to put science on the map for the general public. Around the same time, a Dutchman, Antoine van Leeuwenhoek, developed a different type of microscope. He was a guy who actually made drapes and materials for drapes for a living, but in order to understand the threads in the drapes to better detail, he made a microscope that far surpassed even Hooke's microscope. And with that, he looked at like the tartar on his teeth and saw little tiny objects inside of that, which were actually single cells. And so he's called the father of microbiology as a result. But so he saw many things that even Hooke or nobody else had seen. And again, everywhere he looked, he saw new stuff. He did tons of papers that he sent to the Royal Society. In one case, when he showed those single cells and put that in a paper in the Royal Society, they didn't believe him. And they sent a delegation then to his office, and he showed them, and then they were believers. So he was amazing, but he was also, in my opinion, not a good role model, because what he did was he lied about how he made his microscope in order to maintain a lead. So he made everybody to believe that what he made is these tiny, tiny balls of glass, and then used that. So in this thing here, what this screw is just to hold the sample, and this little circle here is a ball of glass inside a brass plate. And he would hold that up to the sun for illumination, screw up the sample until it was at the focal point of the lens, and look at that. But the way he made those lenses wasn't by grinding them. He took a glass rod, put it in a flame until it was soft, pulled it like a piece of taffy, so it was just a thin thread. He would take that thread, put it into the flame, and it would ball up into a little ball, and he'd break that off, and that was his lens. And so he had a huge lead on everybody else. And he went to his grave with that knowledge. And as a result, it was going to be 150 years before anybody made a microscope that again would have the resolution of his. So the first challenge that immediately hit making a better telescope or a better microscope was the same, and it's the fact that different colors of light don't focus to the same point through a lens. That's called chromatic aberration, as you can see in that weather vane here. So the astronomers figured out how to deal with that first, and the moral of this talk is going to be nothing more than I can say this because I'm a microscopist, but microscopists are the retarded stepchildren of astronomers, because we do everything they do 50 years after they do it first, and then we steal it. So the first way they got around this chromatic aberration was that aberration is less severe the longer the focal length of the lens. So make a two-lens telescope where the focal lengths of the two lenses are big. Yeah, goddamn big, 64 meters. So what they would do is, this is Huygens, who was able to first see the rings of Saturn. He had one lens on the end, on the top of a flagpole with a universal joint, and then he'd have a string that he would yank on while he had the other lens in his hand. And he's going like this, 64 meters, folks. This is not a short distance, and looking like that. And with that, he was able to make this drawing of the phases of the rings as they go around Saturn's orbit. But it was a bitch to work with, but nevertheless, its resolution was about 1 arcsecond, which would not be exceeded until about 1990. So there were other telescopes that had much bigger pupils that are coming up, but as you'll see, aberrations of the atmosphere were limiting. And so really, without adaptive optics, which I'll get into, this is about the limit. But he hit that in 1659. So as usual, Newton discovers creative solutions to get past limitations. He first did his experiment with prisms to understand the dispersion of glass and how different colors are separated. And he said, well, that problem is because of dispersion that happens going through, but if you reflect, then you don't have that type of dispersion. So why don't we use curved mirrors instead of shaped glass in order to focus light? And so he made a reflecting telescope, which was a huge advance. He also developed means of polishing the mirrors in a way with interference. He didn't know it was wave-like interference at the time, but he was able to use this Newton's rings that are a result of interference to use feedback when he's polishing to get the correct spherical shape of his mirror. So these mirrors were now much smaller than, of course, a 64-meter monstrosity. It was simple, it was small, it was stable, it had no chromatic aberration. But at the time, the only way they could make mirrors is by this combination of tin and copper called speculum that would be about 80% reflective, and you'd have to polish it, and then it would tarnish in a few days, and you'd have to polish it again. Astronomers had to deal with this for 100+ years. It was a pain in the neck, but it was the best way to get a reflective surface. But there's another problem, which is that when you have a it's easy to polish a spherical depression, but the problem is then the rays don't all come to one point, because the rays only come to one point when it's a parabolic surface. Then it goes at the foci of the parabola. When you have a spherical surface, you get what's called now spherical aberration. So we've dealt with chromatic aberration, now we got spherical aberration. There's something similar that happens with glass lenses as well, and it was a problem. So ultimately, the guy who invented an octant for navigation figured out a way of grinding a parabola on the lens, and then he had something that was 1.5 meters long with his mirrors that then finally equaled what Huygens could do with that crazy thing 100 years earlier. So the telescopes started to get better and bigger with these mirrors. By far the most important practitioner in the 18th century was William Herschel. He was a composer and a musician who eventually moved from modern-day Germany to England, where he started on the side just doing his own observations of stars with telescopes that he made himself. He was an amazing man. He worked with his sister Carolyn, and he was the workaholic of all workaholics, because what he would do is he would take these mirrors, and he would have, a 4-foot size mirror, and he would spend 8 hours a day. He would have 2 mirrors, one in the telescope, which is not yet tarnished, one that is tarnished, and he has to go around and around and repolish this thing while his sister is feeding him sandwiches while he's doing this for hours on end, because if he lifts his hand, it'll ruin the finish or the figure of the mirror. And he does that during day, and then he goes out at night with the other mirror that's in the telescope, and he makes his observations, and to keep his dark adapted eyes, he would yell to his sister inside of the house, who's there with a candle, writing down all of the measurements of what he sees. He tremendously expanded the universe. He discovered Uranus, the first planet to be seen since antiquity, moons around Saturn and Uranus. He found the first binary stars and saw how they orbit each other. He saw all these fuzzy features that weren't points, which he called nebulae. Some of them are nebulas now, some of them are galaxies or other things, and saw the Mars ice caps. So incredible history of discovery in astronomy with this crazy telescope that he made himself. Now, one of the things that you're going to hear in this talk over and over again is that most everybody who moved the needle from the dawn of both of these techniques up until the 20th century were not trained scientists. They trained themselves. They were often in other professions making money other ways. And they did this stuff as a hobby, but they ended up being the people who really moved the thing forward. So how do we get past, we got a way to get past the problem of chromatic aberration with mirrors, but the mirrors have this tarnish problem. How do we is there another way to get around it? Well, Newton claimed that there was no way to get around this problem of chromatic aberration, and as a result, this is one of the few times that Newton was wrong. And because everybody said, but Newton said it couldn't be done, it took a while before people realized that if they used 2 different glasses of 2 different refractive indices in the right amount and the right curvature, they could balance the amount of dispersion happening from the different colors and get them all to come to a common focus. So Chester Moore Hall, who was actually an attorney, was the first guy to figure that out. So he wanted to get that made, so we contracted that out, but he sent it to 2 different opticians to grind the 2 different lenses that get cemented together, because he wanted to keep what he was doing a secret, and he didn't want them to figure it out. Well, those two opticians subcontracted it to a 3rd optician, the same optician, and then that optician did the work and said, oh, I know what this is for, and then that's the guy who made all the money out of the thing in the end. So eventually, this was put into telescopes. It took a crazy long idea before really the achromatic lenses was introduced into telescopes. Part of the reason is the second material, that's flint glass, was not widely available, but eventually John Doland was able to do that. He was an optician, and so he did the first achromatic telescope, which really pushed the needle forward for now lens-based telescopes instead of reflector-based telescopes, although still the biggest and best telescopes of the time were still the reflectors. So again, it took a long time before, another 50 years, for whatever reason, before Joseph Jackson Lister decided to take this idea of chromatically corrected lenses and apply it to microscopy. So he was actually a guy in the wine business, and he wanted to understand the fermentation process and so forth. So that's why he got into microscopy, and then that led to his innovations there. And eventually also he then spun off a company who was then doing achromatic microscopes, and that really moved the needle forward for microscopy. But the other thing that he learned is that instead of taking those 2 lenses and cementing them together, he could actually change the amount of spherical aberration by their separation. So at that time, he just cemented them at a certain distance. But eventually, as manufacturing capabilities became better, people made various screw-type arrangements to adjust on the microscope itself the separation between the lenses to balance out the spherical aberration that happens in these glass lenses. And so if you've ever used a high-end microscope, you'll see there's something called a correction collar, which does exactly that. You twist that around until you get rid of spherical aberration. As a result, by 1830, by having the spherical aberration corrected and the chromatic aberration corrected, they finally had microscopes that was able to meet what von Leeuwenhoek was able to do with the single ball microscope 150 years earlier. So they got the resolution, but they got a lot more than that, because the problem with von Leeuwenhoek's microscope is because it is a single ball lens, the field of view, how wide an area you have good resolution over, was incredibly small. Whereas with these modern microscopes, the field of view covers then many cells instead of just one cell or a fraction of a cell. So microscopes then finally became semi-scientific. They continued to improve. They were widely used in industry and science everywhere in Europe through the 19th century. One of the manufacturers of them, and there were many manufacturers at that time, was Carl Zeiss. He had a workshop where he sold first single ball microscopes because they were easy to make, like von Leeuwenhoek's, and he sold a bunch of those. And then eventually he wanted to get into compound microscopes, again for the field of view and so forth. So he started to do that. And while the ball microscopes were fairly easy to produce, he had a procedure to make the compound ones, but the yields of good microscopes and good objectives was very low. And he was a demanding guy. So he would have a whole workshop full of people, and he would go around while they're working on it, and a guy makes an objective for a microscope by one of the workmen. Zeiss looks at something through it, and if he didn't like it, he would take a hammer and just bang and crash the whole microscope to pieces in front of the guy. So he was a tough dude to work for. So he got frustrated enough that he contacted a physicist at the local university, Ernst Abbe, who was studying light and studying diffraction, and at that point electromagnetism was a thing, and people knew about waves. And so Abbe developed a whole theory of about exactly what refractive index of different glasses you would have to have, in what curvatures and what spacings, to immediately cancel out all the aberrations to get the perfect image. And furthermore, he said that, well, because of this wave nature of light we know about now, you can never get a true perfect image. You can only get an image that's down to about half of the wavelength of the light you use. And that was known as Abbe's law. Okay. Despite my getting a Nobel Prize for breaking Abbe's law is as sound as ever. What we found is a loophole around Abbe's law, but it's still true that by waves you can only see half the wavelength of light and resolve that. So now Abbe had this total theory. He goes back to Zeiss and he says, "Here, do this." And Zeiss says, "Great." And so they start making things exactly to Abbe's specifications. And sometimes it worked. It was a little better than just the sort of, trial and error method he used before, but oftentimes it didn't. And scratching their heads, why? My theory's right, why? And then they realized that, well, the glass isn't in reality exactly the refractive index or exactly the uniformity that you're saying in your theory. And so they said, damn it, the glass isn't good. So they hired a chemist, a guy named Otto Schott. And then Schott started to develop glasses specifically for microscopy that had exactly the right uniformity and refractive indices to do that. And then all of a sudden, boom, the yields go to 100%. All the microscopes can reach the diffraction limit. And Zeiss takes over the world of microscopy, and they're still at the top today 150 years later. Despite being a bastard as a person at the time, he also set up Zeiss as a foundation, not a corporation. He was the first guy to offer a limited work week. He also offered minimum wage salaries for people. He invented a lot of different worker rights, despite all of that exists to this day. And Zeiss Foundation still, all the stuff you're hearing about NVIDIA and the GPUs and all of that, well, where the hell do they come from? They come from TSMC in Taiwan, okay, who can now make these 5 and 3 nanometer line widths by using gigantic lenses, optical lenses that take EUV light and then do photolithography. Where do those lenses come from? Well, they're in a system built by ASML in the Netherlands. Where do they actually get their lenses from there? They go back to Carl Zeiss and Oberkochen. So there's this whole chain still of all of this supposedly old technology, which is leading to absolutely cutting edge stuff that's happening in science and technology today. So since that time of having that diffraction limit, the optical microscope has been really a workhorse of biological discovery throughout the 20th century. Now, the telescope still had some room to grow because there wasn't a fundamental limit to it. People got, as Schott and others were able to make better and better glass, the speculum mirrors were really a problem with their tarnishing. And you don't have a problem of having to constantly take your telescope apart if you have glass lenses. And so there was now a return of the great refractors. Big ass lenses like this, okay? Some of these weigh tons, okay? And so the Lick telescope and then the Yerkes telescope. Yerkes is probably the crowning achievement of the refractors at the time. Biggest pupils, the most resolution. These microscopes were both in scientific use for nearly a century before they were retired. And other bigger ones came along, but they were still scientifically valuable for a very long time. But then other unrelated innovations started to impact both astronomy and microscopy. The first was photography. You know, the signals from stars are pretty damn weak, and so it's nice if you can do a long exposure to see things. And so that became very transformative almost immediately in microscopy, as they had silver bromide and things like that to do this stuff. And then eventually what happened is they developed for astronomy the ability to go back to reflecting lenses, because instead of speculum, they could actually shape a mirror in glass just like you would shape a lens, but then in a vacuum chamber do silver deposition of silver into a very thin uniform film, which was developed in the mid-19th century, but then was at scale to then make reflecting mirrors that didn't tarnish and could be put in once and for all. And that was the final death knell for the refractors, and the reflectors took over. So first you had, like by 1908, the smaller Hale telescope, and by 1917 you had the Hooker telescope, and the Hooker was a really big important deal because with the Hooker, well, this is the Hale, but I'll say with the Hooker, Edwin Hubble was able to look at these Cepheid variable stars, which basically have a relationship between their luminosity. They pulse, okay? And the period of their pulsation is proportional to their brightness. And so this could be used as a distance ruler to tell how far apart things were. So Henrietta Leavitt was the first who studied these Cepheid variables, and then Hooker applied this as a distance ruler. Not Hooker, Hubble applied this as a distance ruler. And so what he found was, at the time, everybody wondered, is the Milky Way the entire universe? Is everything like Andromeda and all these other nebulae inside of the Milky Way? Well, he started looking at Cepheid variables in the Andromeda Nebula, as it was at the time, and found out that the damn thing was, a million light years away. So all of a sudden, boom, the conception of the universe just grew tremendously. And he also found, as he looked more, that galaxies that were further away were receding faster. So this was the beginnings of the data that ultimately led to an understanding of the Big Bang. So this was all started by this Hooker telescope, which actually is still in use now. In fact, not only is the Hale for rent, you can actually yourself rent either one of those microscopes or telescopes for a night and do your own stargazing to this day. So ultimately, this led to the final biggest dinosaur, but also a very important microscope, which is the Hale telescope, which shortly after World War II was dedicated. That's the primary mirror. Here's people at the dedication. That gives you an idea of the scale. So here you're also starting to reach physical limits of the warping of the mirror under gravity when it's in its mount. And so that's about as big as you can get in a single piece mirror. As a result, telescopes after that stuff are now in sections that are actively controlled because this passive large thing is just at the limit. But for 50 years, the Hale telescope was the largest telescope in the world. When I was in high school, I had pictures like this on my bedroom wall and dreaming of the day when I could be contributing to such pictures. So the next big advance for both microscopy and astronomy was not just taking pictures, but taking pictures that are digital pictures that can be both sensitive and then analyzed for what's inside of them. So that revolution happened when Boyle and Smith at Bell Labs were trying to study these charge-coupled devices as a possible data storage technology, but realized in the end that eventually they could be used as sensors for light. And this shows the kind of imaging at the time that was available with photographic film at long exposures, and this is the sensitivity they had with CCD chips. So it was a complete revolution. It's equivalent in terms of sensitivity to increasing your mirror diameter tenfold. So you're not getting better resolution, but the sensitivity to see dim features just went up like crazy, and that led to the Nobel in physics in 2009, very deservedly so. Now, having CCD cameras also led to a revolution in microscopy because no longer were people limited to just making drawings or single frames from photographic film. They can understand life the way it should be studied, live. And so they could take movies, as in this example, using digital interference contrast to look at these dividing cells on a cover slip. So now all of a sudden, microscopy has the temporal dimension into it as well. But as far as both of those fields got, they were by the 1950s and beyond limited by a common problem, just as they were limited by spherical aberration and chromatic aberration. They were next limited by atmospheric aberrations, or in microscopy's case, sample-induced aberration. So in astronomy, the problem is you have your galaxy that's 1 million light years away, and those light waves come as perfect spherical waves out from their source until the final freaking 100 miles when they hit the atmosphere, and the different refractive indices of the gases in the atmosphere end up creating aberrations, distorting the light. So instead of having near flat wave fronts at the atmosphere, all the waves get bent different ways by the different refractive indices and give you a scrambled wave front, which gives you a crappy image in your telescope. And now your point source star looks like that inside of your multi-million-dollar telescope. So how do we deal with that? So it's like water on the windshield. You have to get rid of that distortion that's occurring. The same problem happens in microscopy. If I look at, say, a fish that's transparent at the surface, I can get good resolution. But as I go in and I go through different cells with different refractive index, as I go deeper, 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 my resolution gets worse and my signal gets lower. So how do I get around this? Well, they have common solutions. The first is to get rid of the aberrations. So in astronomy, the way you do that is by putting your telescope in space. So the first of those was the Hubble Space Telescope, which, as you can see here, looking at the Crab Nebula, even though it has a mirror that's only half as big as the Hale telescope, the data is much crisper because the Hale has to deal with the atmospheric aberrations and the Hubble does not. So it's 10x better than the best uncorrected ground-based telescopes. The only problem with that is that when you polish your mirror to the wrong figure and you end up having a shitload of spherical aberration as the Hubble did, you're in hot water until you convince NASA to spend another $1 billion to send up a repair mission to basically then put in a corrective lens to then recover the way the Hubble was supposed to be. But once they did that, the Hubble took off, and it was an amazing tool. It still is an amazing tool of scientific discovery. This is one example where they took a part of the sky which was completely dark, a tiny little patch of sky when you looked at it for a short period of time. And they let the Hubble integrate signal in that area for 2 months, I think it was, right? And this is called the Hubble Ultra Deep Field. And in the end, when they look at that dark patch of sky, what do they see? It's filled with galaxies. So they were able to look all the way out to about 13 billion years, or shortly after the Big Bang. And so they saw, the estimates now, you have 1 to 10 trillion galaxies with 100 billion stars each, so you have somewhere between 10 to 23 to 10 to 24 stars at this point believed in the observable universe. Well, you can also play the trick of getting rid of aberrations in microscopy if you're willing to look at fixed and dead tissue by putting in different chemicals which homogenize the refractive index. And then once it's homogeneous, then the aberrations don't exist anymore and you can use your microscope to look in. This is an example of looking at a section in the brain of a mouse. What you're seeing are the tubes are dendrites here. The little lollipops are synapses, which are the connections to other neurons. Those other neurons, the parts that connect to the dendrites, are called axons. Those axons can convey electrical signals to the dendrites, and because they have to do that, they need insulators around them called myelin sheaths. All these pink tubes are the myelin sheaths. This represents 1/1,000,000th of the volume of the fly brain. And if you do the math, you say that if you look at a human has 100 billion neurons. Each of those neurons has 10,000 synapses. So 10 to the 15th synapses in a human brain. There are 8 billion humans on Earth, so there are about 8 times 10 to the 24th collective human synapses. So collectively, humanity has more synapses than there are stars in the observable universe. That tells you how complicated a piece of matter is stuck in between your two ears. So what if we don't want to put our telescope in space, because there's a limit to how big of a mirror we can fit in our rockets, and it's super expensive. And then what if we want to look inside of living systems, whole organisms, because cells didn't evolve in cover slip? What if I want to do high resolution subcellular imaging in tissues where the cells actually evolved? How do I get around it? Again, a common solution, and that solution is adaptive optics. I first learned about this when I was an undergrad at Caltech, in which I took an elective optics course by a guy named Bill Bridges, who was also collaborating with Hughes Research Corporation. And they were working on, at that time in the early 70s, laser weapons. And he did this demonstration where he had this device called COAT, which was a bunch of mirrors that could flex together. He would bounce his laser beam off of that. He would have this hair dryer creating roiling hot air like you see on the road on a hot day. And behind this, a model of the Starship Enterprise. And you try to shoot the laser beam through that hot air at the Enterprise, and all you see is this horrible, ugly speckle pattern. He would turn on the mirrors that would then correct, and bing, it would lock on the bridge of the Enterprise, and you move it around and follows along. That really affected me deeply. And I said, this is amazing. And it's one of the reasons I went into optics. And adaptive optics has always been in the back of my head as something I wanted to do. Well, what they do now with modern telescopes is they shoot a laser into the stratosphere to excite sodium atoms in order to create a bright artificial star next to the very dim astronomical object they want to study. The light from both of those things comes back through the atmosphere, is therefore aberrated in the same way, goes into the telescope with an aberrated wavefront, bounces off a mirror that can change its shape, goes to a beam splitter to pick off the light from the bright guide star, which goes into a sensor which looks at that distorted shape and figures out exactly what the aberration was, goes in a closed loop in a computer, which then changes the shape of the mirror to exactly cancel out that distortion, so that the light from the dim object that then goes to your camera is now corrected and back to the diffraction limit. So that's adaptive optics. And so this is showing at left without adaptive optics, that star, and at right with adaptive optics. This is from the Keck telescope in Hawaii, which is still the best ground-based telescope with adaptive optics, thanks to delays in better telescopes that should have been around already. This is without Saturn, without AO, with AO. This is looking at the center of the galaxy. With AO, they were able to see stars circling a supermassive black hole that was at the center of the galaxy. That one also led to a Nobel Prize a few years ago. This is looking, even with Hubble, which doesn't have aberrations, the picture with Keck is better in the infrared because the Keck has a bigger mirror, and if you don't have aberrations, then it's the size of the mirror that matters. We can do the same tricks in microscopy. So in this case, we use something called a 2-photon laser because it can create just a very tight point of fluorescence inside a biological specimen, which we can use in a guide star. Other than that, everything is exactly stolen from what the astronomers did in terms of the deformable mirror, the Shack-Hartman wavefront sensor, and all the rest. And with that, you see you go from no adaptive optics to adaptive optics, no adaptive optics to adaptive optics. You get back to diffraction limited resolution. So now you can understand and study the dynamics, subcellular dynamics of cells, not artificially on a cover slip, but inside of the organism which they evolved. So the next thing, which has analogies between astronomy and microscopy, is planetary astronomy. So, okay, so we're limited in the size of the telescope that we have, so we can't make a bigger pupil, so what do? Well, decrease the focal length by getting up close to the thing that you want to study. Doesn't work for galaxies and stars, but it works for planets. And so we started that way with first in the moon. And this is 1967, being able to, of course, see, this was one of the reconnaissance missions leading up to the Apollo landings to find nice flat and smooth areas to land a lunar module on. Now today, of course, we send things all throughout the solar system. This is the Cassini orbiter, which finally met its maker a few years ago, but man, was it a workhorse. I loved going onto the NASA website and looking at the latest downloads from Cassini, because it was amazing. And you know, many of the things, like there's a tiny, tiny little dot here in this image, which is actually Earth is seen from Saturn and its rings. So it was just an amazing tool for discovery. So there's an analogy for this in microscopy of getting up close and personal. And remember I said there was Abbe's limit, that we can't see smaller than half the wavelength of light. Well, how much of a limitation is that? Well, let's say we want to understand things at the level of the individual molecules inside a cell. If that's a protein molecule, then that fuzzy blob is what you would see at the diffraction limit. In other words, it's about a factor of 100 too coarse to get down to the level of single molecules. So the idea I worked on in graduate school was to create a small aperture in the end of a sharp tip. You shine light down through this tip. If this hole is smaller than the diffraction limit, you can still get light through it. Not a lot, but you get some light through it. And if you're close enough to the specimen, then you can drive that around point by point and get an image where the resolution isn't limited by the wavelength of light, but just by the size of the hole. This doesn't really break Abbe's limit. It's just working in a regime where Abbe was looking at propagating light, and in the near field, where you have these evanescent fields, they convey information beyond that diffraction limit. And I used that when I went to Bell Labs to, at one time, had a world record for data storage using near field storage, did the first super resolution fluorescence imaging of fixed cells, and then hit a brick wall because it's not good for being able to look over whole cells, because the light that comes out of that hole spreads so rapidly that you lose the resolution very quickly. So we needed to come up with different ways to see past the diffraction. Well, astronomers had this same problem too. I don't care whether you fix the aberrations or put your telescope in space, you still are limited by the size of the mirror. So what do? How do we see beyond what we can pay for in terms of the size of a mirror for astronomy? Well, I use tricks. I mean, there are very few planets for exoplanet discovery where the planet is far enough away from the parent star and yet large enough to emit enough light to be able to resolve. There's a few examples of that. These are these little red guys here in the total number of exoplanets found, but they're not common. So you have to find different ways of beating the diffraction limit in some way and pulling out information that you don't have because of the limited resolution of your telescope. One of the first ways to do that is when the planet orbits the star, it tugs on the star, and so the star is moving a little bit toward you in one part of the orbit, and the star is moving a little bit away from you in the other part of the orbit. Now, we may not have spatial resolution, but one thing astronomers are really good at is spectral resolution. So what happens is when it's moving to you, there's a small Doppler shift, which is blue shifting that star, and when it moves away from you, it's red shifting that star. So seeing these very small oscillations in the spectrum of the star tells you that there's a planet orbiting it. So the other way that people often do it, which is now much more common, is they look at when the planet eclipses the star reduces in brightness slightly. Now, of course, the planet is much smaller than the star, so it's only a small change. But as it's doing that transition, you can watch the slope of that transition. That tells you the diameter of the planet. And by how long it takes and so forth, you can determine the size of the star as well. And so what you end up getting with that technique is a lot more discoveries, because in 2009, we put a very inexpensive space observatory, the Kepler Space Observatory, which is an unwinking CCD to look at thousands of stars and look for these small dips in signal. And that became by far the most productive way to detect exoplanets orbiting stars other than our own. So the other possible way to get around this idea of a diffraction limit, the other trick, is something that we developed later, which is, again, if this is the single molecule and the tiny dot at the center is the actual molecule, and this is its image, the problem in a normal biological sample is there's lots of protein molecules. So there's going to be lots of fuzzy blobs that overlap at the diffraction limit. But my friend Harold Hess and I, in 2005, heard about a new type of fluorescent molecule which doesn't just glow when you put blue light on it and glows green. Instead, you have to activate it with violet light. And once you do that, then it'll glow green if you shine blue light on it. And it occurred to us that this would be a way of cheating Abbe's limit, because if you turn the violet light down so low, you only activate a few molecules at a time, and statistically they're going to be separated by more than their fuzzy blobs, so you're still able to find the center of those fuzzy blobs. Turn off those molecules, turn on another subset over and over and over again, and eventually go from an image like this to an image like that. And so we were, as I said this morning, and as Johannes was just mentioning, this has excited us greatly. The only problem is at the time, I was unemployed for a number of years, and I had convinced Harold to quit his job. And so we were both looking for an idea. When we heard about that photo activation, the idea jumped on our hook, and we said, okay, this is what we got to do. So that was the good news. The bad news is we were unemployed. The other good news is this is ridiculously simple. And when I left Bell Labs, I told them all to go to hell, but Harold's smarter than I am, and so when he left, he was able to take all of his equipment with him. So we pulled that out of the storage shed, literally a storage shed like, all those, where you put your old mattresses and crap, and put $25K each of our own money on it. It was good at this time. eBay was a thing, and so you get all sorts of old labs that had gone defunct. You could find old stuff and so forth. And so actually most of our money was probably more for patenting than it was for building the microscope. And so we built that thing in a couple months, and we shipped it to NIH. And you go from, this is a small section through a cell, looking at something called a multivesicular body at the diffraction limit, and the resolution we could get with photo-activated localization microscopy. Or to better appreciate the resolution gains, it's like that with a microscope you can make in your living room. And to my vast surprise, less than a decade later, that led me to a Nobel Prize, which was still hard to believe and still in my opinion, I'm not sure justified, but that's a different story. One of the most useful, and probably not one of, definitely the most useful application of photoactivation has been not for looking at the structure of samples, but instead of understanding the kinetics of single molecules in living systems. So here you photoactivate a subset of cells and watch how they move under Brownian motion, how they stick to one another, and so forth. And so this is an example looking at a protein which is highly diffusive in the plasma membrane of the cell versus one that aggregates the protein and forms virus-like particles. In an example with collaborator Janelia, we looked at the protein involved in Huntington's disease, where the wild-type protein in this nucleus forms tiny little aggregates that are not stable to these very large aggregates that you get when you have this mutation in that protein. And we found by two-color labeling that these little purple fireflies are transcription factors which are needed to create RNA off of the DNA, and then that RNA ends up creating proteins that the body needs. And by actually trapping these transcription factors in these things, it means that certain proteins are not able to be created in the amounts the body needs, and it can lead to diseases. The other thing that happened is that it overturned the model by which people think that this process, one of the crowning achievements of 20th century biology, molecular biology, is something called the central dogma, that you have DNA, but every cell has the same DNA, so why are cells different? Because only different genes on the DNA are translated into proteins in the end through an intermediary called RNA. So this is some molecular simulation of supposedly how a polymerase molecule moves along the DNA and spits out this RNA. You'll see I've seen these simulations for many years, and they always piss me off because it's obviously a ridiculous cartoon. You look at this thing moving along here, spitting this out, and you saw how these little yellow particles, look, it's getting hoovered in. What the hell is hoovering in all of these things? What the hell is going on? Is this magic or what? Is there a magnetic field? What is going on? It's clearly bogus, okay? It's wanting to believe you understand what's going on when you really have only the tiniest clue and 99% no fucking clue as to what's going on. And that's where we are today. And so part of this structure that was built up was this idea that in order to recruit that polymerase, all these transcription factors I just mentioned had to come together one after another to form a complex called the transcription initiation complex. This is all figured out through biochemistry, that this protein interacts with this protein, interacts with this protein. That's all true. But after that, the biochemist, he doesn't have any physical pictures. He's going off his imagination as to what happens and how these things go together. A lot of what you read in your biology textbooks at the subcellular scale is taking structural biology, molecular biology, and biochemistry. All of that data is true. But where they go from there into these types of pictures in the mind are really fantasy. I mean, it's like phlogiston. I mean, it's at that level. So what we found instead of this stable complex, when you look at it with single molecule tracking, you realize that those molecules don't stick in one spot for any length of time at all. There's no time for it to form a stable complex. Instead, what happens is that there's many copies of each of those components of the transcription factor that are hovering around the start position of the gene, and statistically they come on one after another until they recruit the polymerase and start the RNA process. Well, why the hell, if there's Brownian motion, would they all come to one spot? What's the magic of that? Just like this hoovering. Well, turns out those transcription factors have a part on them that is intrinsically disordered. Now, all the AlphaFold and all the cryo-EM and all the X-ray crystallography you've ever seen is all based on crystallizing proteins or looking at proteins that supposedly are identical to one another. Well, that's fine if you have a conformation that's the same all the time. That's not the way proteins work. And also, they have these disordered regions which you cannot see in a diffraction pattern from X-ray crystallography from particle averaging, because it's different in every particle, so they're invisible. And it turns out these intrinsically disordered regions are exactly what creates a difference between proteins that cause proteins to have different binding coefficients to one another or other targets and create these hot spots that then enable transcription to take place. If you cut those intrinsically disordered regions off, you stop the process. Well, there's certain diseases in which these intrinsically disordered regions have been, by mutation, added to transcription factors that shouldn't have them. So, for example, this childhood cancer called Ewing sarcoma, which is fatal. And in fact, my collaborators did an experiment where they cut off the IDRs in single cells, and they showed that they can recover non-cancerous cell phenotypes. And so, well, you can't cut off these things in a human, so what do? You try to find drugs that can do effectively the same thing by rebalancing the stickiness coefficients that happen from these intrinsically disordered regions. And so that led us to start a company. So in 2019, we started a drug discovery company that uses single molecule tracking to be able to screen different chemical compounds to understand these binding coefficients, which underlie a variety of different diseases. Now, it's still too early to tell if this will pan out or not, but I can tell you they're making significant progress in the understanding of this sort of stochastic level of how single molecules self-assemble inside of cells. So the other thing that's really different between astronomy and microscopy, where this analogy breaks down, is yes, there's things happening in planetary astronomy, but by and large, the universe is a pretty static place on human timescales, whereas in biology, dynamics is everything, okay? So like I say, the main tools that were used in the 20th century were these three, but they're all about grinding up the cell into pieces and looking at its components. And the problem with that is, same thing if I want to understand a car engine from a random pile of engine parts. That's what 20th century has given us. These are all the crazy little simulations and stuff we're trying to do that are fantastical. But ultimately, the best way to understand a car engine is having some knowledge of the parts for sure, but actually watching the engine in operation to be able to reverse engineer it. So my point is, how can you understand life without looking at it live? And so I developed a tool when I got frustrated with single molecule localization that used non-diffracting Bessel beams in order to create a sheet of light which would go through specimens to look at them at high speed, low toxicity for long periods of time at high resolution. And this has been, in my opinion, even though Palm still gets the vast bulk of the attention, going to be in the long term the most impactful instrument I ever make. But we want to apply it to multicellular specimens because cells can evolve in cover slips. So how do we do that? Adaptive optics. So we combine the adaptive optics that I described previously with, for both the excitation light sheet that comes in, the detection light sheet that goes out. We've applied that to many systems, and it's a whole new universe at our disposal to study. I mean, I feel like Galileo when I use the lattice light sheet and the lattice light sheet with adaptive optics, because I'm seeing life in a way that nobody has ever seen before, just like Galileo seeing the Galilean satellites. We can't make sense of it all, but it's important. So what comes next? Well, for astronomy, it's bigger and better telescopes. Sadly, when I first wrote this talk, probably 10 years ago, this stuff was imminent. It is still imminent. So 30-meter telescope, who knows where or when it will come to fruition. The Webb, thank God, finally made it to, and didn't break on its way to L2. But now it's going to be an amazing tool of discovery. Europe, not to be outdone, has been working, and thank God doesn't have the problems the 30-meter has. And 2028, I don't think that's going to happen. I think they're talking at least 2030. But it will also have multi-conjugate adaptive optics with multiple lasers to be able to correct over a wide field of view, which is the problem with AO in astronomy, is the isoplanatic patch is so small, you're looking over a very small region at a time. But if these telescopes get off the ground, and as I said to some of you at one of the things I had today, I don't think astronomers has taken seriously enough yet the implications of SpaceX and Starship. When Starship is flying, it will completely revolutionize astronomy. It's going to reduce by a factor of 100 the cost per kilogram to orbit. You're not going to be making instruments that you have to shave milligrams off of and hence make flimsy and difficult like the Webb. You're not going to be limited in payload size like the Webb and have to have the mirrors that are folded up like origami the way it is. And for planetary astronomy and deep space astronomy, once Starship is running, it's going to be completely revolutionary. There's, you think the best days of astronomy observation are over. They haven't begun. It's going to be amazing. And that would be one area, if I were a physicist, I'd be thinking about moving into going forward. So in the future for us, what's the limit? The limit is we have microscopes that can see what's happening in cells better than anything before. But the problem is these systems are insanely complex. You have 37 trillion cells in your body. You have thousands of different cell types. And each of these cells has at least 10,000 types of protein molecules, 10 billion molecules at all in every cell. Incredible diversity. We can take data that can see a lot of that, but we have no idea how to handle the data. We have, we take, on our modern microscopes, we take 4 terabytes per hour, which is half a petabyte a week. And we can do all the pre-processing in that data, but actually visualizing it and interpreting what you're seeing, not a chance. So that's really the limit. So where we are now is trying to develop, thinking about going away from just writing analytical scripts for every problem we want to do, as in this case, to ultimately adapting AI towards this. I've been the biggest skeptic of AI in my field that there is, but I've learned I'm going to have to dance with the devil, because I think the only way we're going to be able to analyze and interface with the data is through a combination of these transformer-type architectures that have been developed recently by Google for vision, applied by Meta for segmentation. We think about doing a physicist sort of back of the envelope calculation of how much compute would be needed to go from what they have done to our problem. And it's scary. It's probably at the edge or beyond the edge of where modern AI is. But maybe that's a good place to be, because both the hardware and the concepts of AI are increasing in sophistication very rapidly. So maybe the future will be that we'll be able to actually understand the cell, and before I go to my grave, ignite a revolution in cell biology seen inside of the whole organism that will be as transformative as any of the revolutions in astronomy or microscopy to date. But regardless, it's been a real privilege to both be a fan from an early age of astronomy and also a practitioner of microscopy. And while I love all of the technology that goes into these things, I just get a kick out of the beauty of nature at both the large scale and the small scale, and I hope you do too. Thank you very much. Yeah, sure thing. Yep.
We have time for questions for our speaker. Anyone who'd like to ask a question about
anything?
This amazing presentation.
Something I've never understood with telescopes and microscopes is going through the field of vision. So, for instance, in undergrad, I worked with fruit flies, and I used confocal microscopy to look through the different layers of it. And as I was doing it, I still just didn't understand how
you're
we're
seeing
through the muscles and through.
Yeah. So what's happening, like in a confocal, like you described, right, is the microscope itself creates this solid cone of light that comes into a focus, right? In a normal wide field microscope, and with confocal you're usually doing fluorescence, okay? So what happens is that you generate photons going back all the way through this cone, including the parts that are out of focus. And in a normal wide field microscope, that creates a haze on top of the thing you want to see. So you can't look very far in a Drosophila or something before it's too hazy to see anything, right? In a confocal microscope, what happens is all of that light goes back up into the microscope, and it can invert and create a focus again inside of the microscope. Now, all of the out of focus stuff would hit at that plane eventually, but if you have just a black screen with a tiny hole in it, the only light that makes it through is the light that was generated at the focal point. So that's why you can drive this thing along, and as long as the specimen isn't opaque, it can be somewhat scattering, but as long as it's not opaque, the light will still go in, and in the end you'll still get high resolution because it's only letting you see the information that's at that focus and not the blurry stuff everywhere else. Okay. Now, the problem with the confocal microscope, though, is you're still creating fluorescence and you're still illuminating the sample through all of that space. In fact, it doesn't stop there. It's like an hourglass. It then spreads back out the other way, right? And so all of that doesn't make your Drosophila embryo or whatever you're looking at very happy. And so a big advance was these light sheet microscopes, because they bring the light in from the side, and so they're only illuminating the one plane that is in focus, and so you're not generating damage and photo bleaching and those areas above and below.
So you've blended together physics, optics, astronomy, molecular biology, cellular biology. I guess this morning you talked about automotive engineering as well.
That's true.
We talk a lot about the importance and need for interdisciplinary science. And I'm wondering, from your background, if you have any words of wisdom that you could leave us with, or maybe for the students as well.
Well, I would say that almost any advance forward with anything I've done in my career has been by contact with disciplines of which are outside of my previous experience. Another example, coming back to the automotive thing, before I built this crazy machine tool, the first project I did at my dad's company was a machine vision system. So when you make auto parts and you have to machine all these surfaces, drill all these holes, you need to inspect to make sure it's to the specifications the manufacturer needs. And the way they would do it is with these big machines called coordinate measuring machines. They're very slow, and you inspect like 1 in 10,000 parts, and you try to build up statistics to say it's okay. So I said, well, that's crazy. I can just put cameras all over the part right as it's coming off, and I can look at every part that's coming off. And the way I knew how precise these holes were is I used sub-pixel localization using the same techniques that I used for Palm. Okay, so I borrowed this idea of sub-pixel localization that I had from Bell, and I applied that to auto industry inspection parts. It worked great, but in the end, what would happen on the machine floor where they were making these parts in the auto companies is that it was rejecting a lot of their parts. So what they did is they turned it off. And they still had good parts, because what they did, their old solution for that, which is still true today, is what they would do is they would over-spec the tolerance they needed for the parts. And as a result, they ended up getting good enough out of almost all of the parts. But if you actually asked a machine to tell you, is this to that crazy spec, it would say, no, 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 no. So anyway, another lesson learned. But time and time again, you know, again, you know, at Bell Labs, most of what I did with near field was very much, you know, condensed matter physics type stuff and so forth. And while I had this vague idea for the Palm with this, you know, multidimensional localization, it wasn't until hearing about photo activation that it was like a key going in a lock. 90% of the puzzle was there. And as soon as this thing, which, you know, we went to Florida State to see if I could work on my optical lattice microscope, and then this guy hands us the keys to heaven by saying, there's this new type of photoactivatable fluorescent protein, and we're just like, you know, it was totally out of our experience because we don't follow that field at all. I didn't, you know, I remember shortly thereafter saying, we got to work on this, and we got to make these cells that have this stuff. How do we do it? And he says, oh, well, we will transiently transfect it with this. And I say, what the fuck is transient transfection? You know, and so I have to start learning a whole new lingo and learning what, you know, when you pick it up by osmosis and time and screwing with enough biologists and so forth. But yeah, it's fun. So interdisciplinary, totally. I think every advance I've made has been by not just building the instrument, but also applying the instrument, whether it's been, you know, looking at quantum wells or looking at magnetic materials or looking at cells or tissues. And it's fun because, you know, you just pick up. I'm not an expert in a lot of things, but I know a little bit about a lot of things, right? And it's been a ride, you know, because you get to learn. You know, the nice thing about being a tool builder is when you have the one tool, you know, you get to work with some of the best people in the world because, you know, they're all stuck and they need new tools to see their systems in ways. And it's a kick when they're able to get past a stuck and be able to see the things they've studied for decades in a way that they've never seen it before. It's awesome. So, you know, it's this blend of engineering and science that interface is what turns me on. Yeah.
So, I love the fact and the history of how we, you know, explored the space and explored how cells work and also how the atoms and what's inside of it. But something that bothers me is that why haven't we explored too much on what's happening under the sea and what's happening under the earth?
Good question.
Which is responsible for what's it? It's just what's stopping us? What is it that we can do to increase that, or are we just afraid that if you put too much energy, we'll go there? I mean, if you put too much energy in there, it can.
And the mantle will blow up the earth. I don't think we have that capability. I mean, certainly. You know, it's kind of, I said this to one of the groups today, but one of the triumphs of physics is how much we know. The 20th century has, you know, we understand the structure of a neutron star better than we understand the structure of our own bodies. You know, things that we've never had direct contact with, which are millions of light years away, because of what physics has done. You know, we understand to a degree what's happening in the structure of the interior Earth, but I bet you there's plenty of surprises, and geologists find surprises all the time already. And then in terms of the oceans, yeah, I totally think that ocean exploration and ocean exploitation it's 70% of the planet, man, the surface of the planet. You know, there's people who do it, but I think it's probably and so that's the other thing that I have always been attracted to, is finding an area where I feel like people are not. You know, I gave a talk at this Nobel thing about working where others aren't, was the title of the talk, and how I've always been attracted to finding something where I have the space for myself, or there's just very few, and working there. So that's another principle that's guided me. Yeah. I think you had a question? Yeah.
It's interesting, all of this technology, especially the microscopy work long. But one drawback to this is the incredible expense and the availability. Because these instruments are so expensive now, there's limited usage, and so it's hard. So do you see at all that there's going to be some revolution or transformation where these instruments?
I mean, you are preaching to the choir, my friend. So a few weeks ago, I gave a talk at where I have my other lab at Janelia called Confessions of a Frustrated Optical Microscopist. Over much of the last decade plus, more than 50% of the effort of my group has been in getting other groups to be able to adopt the tools we've developed. Cost is one of the factors, but it ain't the only one. Even simpler tools like Palm and so forth, that isn't terribly expensive, get poor uptake. And there's different so I've tried 3 different models. One is open source, one is open access, and one is open wallet. So open access is, and we've done this at Genelia where I used to be, we created an imaging center which is free for biologists anywhere in the world. You submit a proposal, you come, we will even make your samples and prepare them ahead of time so they're ready when you walk in the door. You do a 2-week imaging session, you go, fine. Well, it's gotten a lot of publicity, a lot of good attention. If I look at the 10-year record of it, it's produced probably 3 papers per year, okay? Even though we bring in dozens of scientists. And part of the problem is biology doesn't work in 2-week intervals, okay? You have to be able to do it again and again, like any experiment. You have to iterate it. And the problem is if you have to do another proposal and come 6 months later, it's very difficult to do. And it costs an oodle in order to be vertically integrated and all that. So the second one is open source. Okay, let the biologists have their own microscope. And for example, with my lattice light sheet, we took a lattice light sheet apart in a room that had cameras like an operating theater. Took it apart down to the screws, put it back together, explained every step, ran cells, have 60 hours of video of how to do this that you can watch. We have drawings down to the single screws of what to do and so forth. 140 licenses to get all that information worldwide. I would guess now maybe 40 were built, maybe 10 to 15 are still in use. The problem is misaligned incentives. Okay, so biologist wants a microscope. He's the PI. Okay, what does he have to do? First, he has to now become vertically integrated and have some people in his group who know something about physics and engineering. So he has to find those people. He finds those people. They're usually grad students or postdocs. They have to go up their own learning curve because they're young, and then they start to build the microscope. They don't want to build an exact clone. How is that a PhD, or how is that going to get me an academic job, right? So they have to do some variant, and usually the variant is not even a superior variant, and it's just a paper, right? And even if they do, and even if they succeed and the biologist starts getting data, he graduated or he went on to his career, and the instrument sits there collecting dust because he can't find a replacement. And so that model doesn't work either. And then the third model is open wallet. Well, the advantage of the first 2 models is it generates enough buzz that companies say, yeah, there's enough interest that it's worth putting in the R&D dollars in order to commercialize it. We've done that with a number of our microscopes. And what happens is the sales are very low, in part because they have to recoup all their R&D money, so the initial cost is very high. And then on top of that, the vast majority of biologists, I'm sorry, I'm going to again piss on academia like I've done all day long. The incentives in academia are to publish and get grants. And you can do that fine with a wide field microscope to this day. So a wide field microscope has remained the undisputed champ of microscopy now for 400 years, and it continues to do so because people can still publish papers and get grants. The people who have succeeded and excelled at using these tools are I'm sorry, I'm again going to be very opinionated against academia, but there's a very small subset of people in academia who are driven by the science, really driven by, they don't care about the grant, they don't care, they have a question that's been bugging them for their entire careers. Those are the people who are great to work with, and they will continue to work with you until they get their answers. And so you do move the needle, but you move the needle slowly because of those problems. This is part of a spiel that I've been making other than that rant I gave in that other talk about the problem with my microscopes today is the microscopes are great, but we don't have the tools to analyze the data and extract meaningful insights. So it's a data problem. I am not a data guy, but I'm, as again, about the interdisciplinary thing, starting to be forced to rub shoulders with data people in order to figure this out. It's clear that AI is the only even hope. I don't even know if it's going to succeed, but it's the only hope for a scalable solution to analyze data that we have at scale. But the problem is it's bigger than any problem that's been tackled in AI right now. That's clear. And so What it means is we have big fancy microscopes that have adaptive optics and lattice light sheet that are too difficult, too expensive, as you point out, for an academic center. We have organisms, we need many, many different transgenic organisms to study different things. And we need AI out the wazoo and good AI people on top of it. What does it mean? It means that my microscopes, I've always been a tabletop guy. It means I have to wave the white flag and say what we need is something, a cell observatory. We need basically a centralized facility where, just like astronomers, they come with a proposal, then you point the telescope at the thing he wants to study, and then they can even analyze data for you and send back. I think that's possibly the only way forward in this. As much as I hate big science and prefer tabletop science, I think our tools are reaching the point where it may become inevitable. Very long answer to your question, but set me off. Okay. Yeah.
Hi, thanks for the meeting. So, one question is about the last part. So, how did the AI actually accelerate the efficiency of the microscopy?
Yeah, so there's several steps in what you want to do to be able to understand. The goal is to understand the foundational rules of life, how subcellular things interact to create a self-sufficient and replicating cell, okay? So we can see and visualize the dynamics of all of those components. But again, the data is 5-dimensional when you add in the colors of the different things, and vast. And so the first step in the process is you have to see the cells in tissue to see the native phenotypes. The first step of that process is knowing where a cell begins and ends, so cell segmentation. So there's been lots of AI cell segmentation papers out there already. They all suck. They're 2-dimensional. They are brittle. I believe they can be made robust. Most of them are based on convolutional neural networks, and I think transformers are a better architecture. And I also think that you actually gain in some respects by going to 3 dimensions, because there's self-similarity between different sections as you go through, and 4 dimensions because there's self-similarity in time, there's continuity in time. So all of those things with a transformer model might get us past the barrier of at least initially segmenting. Being able to, even with our own human eyes, be able to see these cells in tissue segmented out and studying them would be a vast step forward, even though it's just the baby initial step. And then from there, it's then being able to classify and the organelles inside of the cell, classify the interactions of those things, so you can start to build up these multimodal foundation models can build up different types of data like that over time. And then in the final science fiction-y analysis, then you add a large language model on top of that, because the biologists can't dive right into bits and so forth, right? Or even any significant complex data. What you want is something the biologist can say, my interest is in cancer metastasis. Please, foundation model, tell me what happens when a neutrophil, which is supposedly attacking a tumor, goes from the blood vessel and has to go through the blood vessel. How does it rearrange its nucleus and its organelles in order to make it through the small constriction that happens there? And then what proteins are involved in there? And now I have this vast database that I've collected of all sorts of processes across organisms over time. Many, many, many petabytes have now been reduced by my A model. It can go through that large language model and can pop up. Here's 5 examples of when, this neutrophil is going through this part and this part. This is what's happening to the mitochondria. That's what's happening to the nucleus. This is what's happening when it happens in these 20 different cell types, and da-da-da-da. So that would be the dream, okay? But that would be so, and then it doesn't just say that and show the pretty pictures. It pops up, here's histograms of the process of how these minor, it would do everything, write the paper for you, for crying out loud, right? I mean, so it sounds science fiction-y, but my dumb thing is I took ChatGPT and I drew a closed shape like this, and I asked ChatGPT, find me the center. Bing, out pops the center of this irregular shape, So that's the goofy baby version of where I think this could go, right? And that would be, again, you want to be able to converse with the data the way humans converse among themselves, because that's the way we interpret things. Yeah.
All right. I think that's enough time for questions, but our speaker might entertain some more if you're willing to
Sure.
come up and talk to him
Yep.
afterwards. Let's thank him once again.